These are the video notes for Objective 1C, piecewise functions. So the first question that we have in our notes is, what is a piecewise function? And we actually have a definition of piecewise as a function defined by different functions for different parts of its domain. So the example that we're looking at is negative 2x plus 1. This is the first function. And this function is only valid if negative 3 is less than or equal to x is less than 1. We have another function, 2. This is a constant function, which means it would appear as a horizontal line on a graph if x is equal to 1. And then we have the function x squared, which is a quadratic function if x is greater than 1. So this is the notation we use for piecewise functions. You're generally going to see a French brace or a curly bracket, and then the functions and the domain. So over here is the domain that it's defined on. And over here are the equations that should be used. So in your notes, you have the graph of this function. And as you can see, there's a line segment produced by this function. There's a single dot produced by this function. And then there's a portion of a quadratic. So it doesn't look that curved, but it is indeed curved, produced by this function. And one thing I want to talk about is the difference between a closed circle and an open one. So when you look at this line segment on the graph, you're seeing something similar to this. And that's because the closed circle is inclusive. And it's used for any time you have less than or equal to, or greater than or equal to, which is what we have right here at negative 3. Then over on the other end of this line segment, you have an exclusive mark, which is the open circle. And this is used anytime you have a less than or greater than symbol, like we do here at positive 1. Now, check the x-coordinates of each of these points. This point should line up with x is negative 3, and this point should line up with x is equal to 1, because that is how the domain is defined in this piecewise function. Now, the one that I said would appear as a horizontal line does not actually appear as a horizontal line in our graph because it's only defined for one specific point, x equals 1. So you can see the point 1, 2 on your graph. And finally, we have our quadratic, which begins with an open circle at x is 1, and then continues to the right for all x values greater than 1. Well, we have two questions based on this piecewise function, and I'm going to answer both questions based only on the equations, whereas you can also answer these based on the graph. So the first question is, what is the domain of the function? Well, this is the domain. So as you can see, the domain of the function starts at negative 3, and it's inclusive, so we would use a square bracket. Then it stops at 1 for this portion of the function and does not include 1. So you would write something like this, except the function is redefined at 1 right here. So 1 would be included in the domain, except the next piece of the function includes all values greater than 1. So what symbol in mathematics do we use to imply all greater values? Hopefully you thought of positive infinity, like this. The domain of this function is from negative 3 until positive infinity. Is this function continuous, or is the graph continuous? And the answer is no. There's a large gap in the graph at x equals 1 where the three functions do not meet up. So if the end of the quadratic started at the end of the line segment, we could say that the graph is continuous. But because you see a huge vertical space between the 2 points, this is not a continuous graph. The first thing we want to do algebraically with piecewise functions is to evaluate them. So using the same example, I'm just going to erase some of my notes from describing a piecewise function because we're using the same equation. This time though, we're going to try to evaluate the function at different inputs. So we have -3 less than or equal to x less than 1, x equals 1, and x greater than 1. We're going to find f of 2, f of 1, f of -4, and f of 0. Well, all of these inputs first need to be found in the domain of the function. So let's start with 2. Is 2 between -3 and 1? Nope. Is it equal to 1? Nope. Is it greater than 1? Yes. So f of 2 is greater than 1, which means it gets plugged into this equation of the piecewise function. 2 squared is equal to 4. F of 2 is equal to 4. Now we need to find 1 in our domain. And 1 is a little bit trickier than 2 because you see a 1 here, a 1 here, and a 1 here. And the difference is between exclusive and inclusive. So for example, 1 is not less than 1. 1 is not greater than 1. 1 is equal to 1, which means we're going to be using this function here. If x equals 1, the function is equal to 2, which means we can say that f of 1 is equal to 2. Where would you find -4 in your domain? It's not greater than 1, it's not equal to 1, and it's not between -3 and +1. So for this one, we would say no solution, because -4 is less than -3, and this function is only defined from -3 until positive infinity. Last one is f of 0. In which of the domains does f of 0 fit? It fits in this domain because 0 is greater than -3 and less than 1. So we're going to plug in 0 to this equation of the piecewise function, which gives me a final result, f of 0 equals 1. Our next example of piecewise functions is how to graph them. So this example has already been graphed for us, and we want to start over fresh with a new graph. Now, in our rubric, we're going to break down the skills of piecewise functions a little bit in depth. For example, to be partially proficient, you just need to be able to graph a linear piecewise function. But to be proficient, you need to graph a piecewise function that includes both a linear and a quadratic portion. So let's write down example 3, which is completely linear. This one only has two pieces, x plus 1 if x is less than 2, and a constant 3 if x is greater than or equal to 2. So let's get a graph of this one working. I have a few tips for graphing piecewise functions. A lot of them involve colors, but you can do this without any color. And the first thing I'd like to recommend is that you mark your domain with either a dotted line or a solid line, depending on if it's exclusive or inclusive. So I'm going to head over to 2, and I'm going to put a dotted line through x equals 2. This is the boundary where one function ends, and it actually marks where the second function begins. So I like to mark my domains as dashed boundary lines to help me graph the function a little bit clearer. Now we need to review how to graph a linear function. So a linear function is in the form y equals mx plus b, where b is the y-intercept, or starting value. This is where you put your first point. And m is the slope, which you graph as a ratio of units up and units over. To graph this one, we need to start at +1 on the y-axis. And since the slope, there's no coefficient here, we say the slope is 1, which means we need to go from this y-intercept up 1 and to the right 1 until we hit our boundary line. At the boundary line, we're going to need to decide to use an open circle or a closed circle, but let's go ahead and graph the rest of this line, because lines are continuous in both directions. I'm just going to extend it out backwards. At the boundary, we're either going to put a closed circle or an open circle based on the less than symbol. Since less than is not less than or equal to, we want a nice, clearly visible, open, exclusive circle. The next thing we need to review to finish this function is how to graph a constant. Constant is one of your families of functions. The image of constant is on your notes for 1b. A constant is a horizontal line through whatever value it has. So we need a horizontal line through 3. Again, we only want this line when x is greater than or equal to 2. So come back to your boundary line and find 3. It happens to be where the other function left off. So we're going to go ahead and fill in this open circle, and then x is greater than 2 are these values to the right of our boundary line. So heading to the right, we're going to draw our constant y equals 3. This example is continuous because this function fills the hole where the other function left off. There are no gaps or breaks in our domain or our range. The domain of this function is negative infinity to infinity because it heads from the left infinitely to the right infinitely, but the range is negative infinity to positive 3 because it won't exceed positive 3 with this horizontal function. Here's your first example of how to graph a piecewise function. Let's increase the difficulty by adding more functions and more types of functions. Example 4 in our notes is f of x equals negative 3 when x is less than or equal to negative 2. It's equal to negative x squared plus 4 when x is between negative 2 and 1, and it's equal to x minus 2 when x is greater than or equal to 1. So the first thing I notice is that this function will be continuous. Has a continuous domain because negative 2 meets negative 2 and 1 meets 1. We don't know if it's continuous because we don't know if there's a break in the range, but we do know it has an infinite domain. I'm going to start by marking my first boundary line, x is equal to negative 2, and I'm going to go ahead and use a dashed line here. And then I need to graph the first function, which is a constant negative 3. So at this dashed line, I'm going to find negative 3, and I'm going to draw a horizontal line extending to the left, because that's where x is less than negative 2. At the boundary line, do I need an open circle or a closed circle? Because it includes an equal to, I'm going to use a closed circle. And I've graphed the first piece of this piecewise function. For the next piece, let's just color code this. I need to graph a quadratic function. This quadratic has been reflected over the x-axis and raised up 4 units. So I'm going to have to pull out some of my 1B skills on how to graph a function. I also want to mark my boundary because this function only exists between negative 2 and positive 1. Keep in mind, to graph a piecewise function, you may need to go past your boundaries just to get the shape correct, and then erase the portions of the graph that you don't need. You'll see me try this technique with the third function. For now, this one actually fits. So we want to think of a downward-facing parabola, but we need to raise it up 4 units. So we're going to go 1, 2, 3, 4. Here's our y-intercept. And then if you remember, quadratics go 1 unit away, right here on the boundary line, so I'm done graphing to the right. And then it goes 3 units away. 1, 2, 3. Or that ratio of 2 squared is 4. 2 over, down 4. We have 2 boundary lines that we need to contend with. So on the left side, or at negative 2, should we use an open circle or a closed circle? This less than symbol is not equal to, so I'm going to erase my mark and leave a nice, clear, open circle. At positive 1, it's also a less than without the equal to, so I'm going to erase and leave another open circle. We've now graphed the second piece to our piecewise function with one piece to go. From our review of linear functions, I know that this is where the line crosses the y-axis, and I know that the slope is 1. The problem is this function only exists after 1, so how do I graph the y-intercept? Well, I'm going to graph the function like normal where it goes, and then I'm just going to erase the portions that don't exist. So we're going to head to the y-axis at -2, and we're going to go up 1 and over 1 until you have enough points to draw a clear slope. This marker's got like every color in it. It's a rainbow marker. So here's our function x minus 2, but it only exists when it's greater than 1. Go to your boundary line, leave a closed circle because it's or equal to, and then erase the little bit of your line that's before the boundary to get a complete picture. Is this graph continuous? And the answer is no. This graph has a gap here at -2 and a gap here at positive 1. The last example in our notes for piecewise function is a story problem. We're required to graph it and write the equation based on the words that we see in the story. So let's take a look at this context and see what we can come up with. An economy car rented in Florida from Enterprise on a weekly basis costs $185 per week. Extra days cost $37 per day until the day rate exceeds the weekly rate, in which case the weekly rate applies. Also, any part of a day used counts as a full day. Write and graph a piecewise function. The first thing we want to do is define our variable. So in this context, we need a way to track and measure how much money we're going to spend, and it seems like the best idea is going to be days. How many days did you rent this car? So let's get an idea of how this function works. I'm just going to make a table, and I'm going to calculate how much this rental car is going to cost me. It looks like I need to pay $185 per week, which means I have a minimum of 1 week. And since I decided that x would be days, I'm going to start my function at 7 days. At 7 days, I am going to spend $185 because it's $185 per week. Then on the 8th day, I pay $37 extra dollars. So I'm going to add 37 to my weekly rate, which leaves me with $222 for 8 days. And I'm going to continue doing that until my cost exceeds the weekly rate. So what does it mean to exceed the weekly rate? Well, I know for 7 days or for 1 week, I'm going to pay $185, which means for 2 weeks, I just need to double that, which gives me a 2-week cost of $370. So if adding my days exceeds $370, I may as well just pay for the second week. I haven't exceeded this amount yet, so I'm going to continue adding 37 until I've exceeded this rate. The 11th day is 333, so we're getting close. The 12th day is 370. Which means that I can assume the 13th day I would also pay $370 because by that point it's cheaper for me to just pay for another week. Now that I understand the problem, how do I write a piecewise function? Well, let's just focus on the number of days between 1 and 2 weeks. So we just want to write our function when 7 is less than or equal to x is less than or equal to 14. We're going to restrict our domain to make this problem a little simpler. Over to the side, we'll say the cost for x days is equal to, and then it's easier to define this portion of the domain because it's constant. I know that I'm going to pay $370 if my days are greater than or equal to 12. AKA days 12 13, and 14. Then what equation do I use up here when I had paid 1 week plus 37 each extra day? Over here, I'm going to write 185 as my starting cost, and then I'm literally going to write $37. To indicate per day, I'm going to put X. And this is when the domain is between 7 and 12 days. But this time, I did not include 12 because 12 is included over here. So this is the piecewise function that defines this relationship. And you can test it out by plugging in different values like 9 or 11 or 13 and making sure that it matches your function. The next thing that we need to do for this problem is graph it. So let's erase the table that we used to understand the problem and leave the function. And let's get a graph. The nice thing about graphing this function is that it is a real-life example, which means the negative quadrants of my graph do not apply because negatives don't exist in this particular context. I'm going to modify my graph a little bit, and I am going to say there's a break, and that 7 days starts right here. 8, 9, 10, 11, 12, 13. 14 days is right here. And then on the y-axis, I am also going to put a break. And since my lowest cost is going to be $185, I want to count by something that can get me from 185 to 370 without taking up too much excess space. So let's try 180. And then every 2 squares, let's put 200. Or 20 more. 200, 220, 240, 260, 280. This is going to exceed my graph. So we need a steeper slope. Let's try doubling and adding 40 each time. 220, 260, 300, 340, and 380. Now remember, whatever you count by is what you have to graph based on. So it's best to pick numbers that are easy to identify your values for. We need to graph this equation, which is starting at 185 on day 7 and adding $37 per day until day 12 when it hits $370. So I'm going to put my y, or my first point, at 7, 185, which is slightly above 180. I am using a closed circle, so that dot will be my final dot. And then rather than trying to do a slope of up 37 and over 1, I'm just going to use the fact that day 12 is $370 and jump straight to day 12, 370, which should be up here close to 380. This dot will have to be an open circle because it does not include that value. Thankfully, in a real-life function, you do see a continuous trend. Right where this function leaves off is where the other function begins. So even though I need this to be an open circle, when I go to graph 370 at 12, I'm just going to fill in the circle. And this function portion stays constantly 370 until 14 days. And there you have the piecewise function that models the cost of Enterprise from Florida. This concludes the video notes for Objective 1C, Piecewise Functions. I provided a few links through the course Canvas page to allow you to practice, and the book problems are also a great way to practice.